All right, why don't we go ahead and get started. So welcome back to E9yv8x8. So just as usual, actually this time there's not really too much logistic stuff because next week is obviously spring break. So nobody will be here. You guys will go party or whatever you go do. But let's say the good and the bad news is I will be posting the next phase of the project fairly shortly. It won't be anything too surprising. So basically, now that you sort of know what the channels look like, I'm going to be posting up sort of instructions on how to actually get to the GPDK basically version of the process they'll be using, which is basically cadences. Just it's a fake process, nothing real, but just you have some transistor models. You can actually run things in cadence and stuff like that. So I'll be posting how you can do that. And really, this next phase of the project will basically be saying that you should go and actually have some certain portion of the link actually implemented by a certain time. I believe it'll be sort of fairly shortly, maybe like at the end of the week after spring break or something like that, or maybe even actually a week after that. Just because basically the following week will be sort of the first round of presentations. So again, there will be nothing too particularly surprising there, just because you sort of have an idea of what's the project all about. But I'll post that up and just kind of give some clarifications and hints and things like that. So definitely be on the lookout for that, just so you can go ahead and really get going. Once that goes up and you actually get a chance in between all the partying you're doing during spring break. So before I kind of dive back into material and stuff. Any questions on the project? Hopefully people actually started looking at it. Everything is clear. No. How many of you guys? Oh yeah, go ahead.
One part where you say like a 2 picosecond timing resolution for the channel response. Was that just for the timing stuff?
Yeah, I mean basically, so that's just essentially how heavily you oversample the response. Right, because you can imagine if you sample it at different rates and then you run some of, for example, either the equalization or in fact even just finding where the peak magnitude is, depending upon how heavily you oversample it, you'll get a very slightly different response. So basically I just put that number in there just so that you can, so everyone's consistent essentially. If you find later that, that number is not quite right or you change that number and you get very different results, then you can go back and revisit it. But I think 2 picoseconds should be sufficient for most things that people are doing. Because if you kind of think about it, at least at 10 gig, that's like 50x oversampling. So that should be plenty. Other questions? I guess I made the first phase too easy. You guys want it harder? Okay, well, so if there's no questions on the project, then what we can do is just go ahead and dive back into the material. So last time we sort of started talking about PLLs. Actually, we spent a reasonable amount of time talking about PLLs. And so the sort of next set of slides that we started getting into were really some more of the, let's say, detailed implementation issues in terms of the specific components that you might find inside of the PLL. So the last one we ended up to start talking about was the charge pump itself. And we drew actually one version of the charge pump, which I'll just kind of sketch it on the side over here. Oh, that doesn't help. We drew one version of the charge pump where basically we had some current source device, and then we had some switch that was either connected to down or up, depending upon which direction you were going. I just want to quickly redraw sort of a slightly different version that turns out to be slightly more common in the let's say most of the implementations that I've seen. So essentially, the way the charge pump is typically done, and I won't draw the full thing, I'll really just draw sort of the output stage, but recall that you really have to sort of match everything up correctly. So this time around, if you sort of think about it, in the one that we drew last time, we put the switch on top of the device. Turns out that oftentimes you'll actually put the switch on the bottom of the device. Okay, so as an example, this will be down, this will be up bar, this will be some bias voltage, and that'll also be some bias voltage. Okay, and then of course this would be your actual charge pump output. Okay. So actually, you guys have any thoughts? What's sort of the trade-offs in doing things the couple of different ways here? Why might you choose to do one versus the other? And by the way, you should start thinking about like second order, well, not really second order actually, but quote unquote second order effects, because remember, this is a pretty sensitive thing that you're going to want to have it be very, very clean, because this is really going to come into the jitter performance of your overall loop. Any thoughts?
That because of the the digital any noise on the digital line will not get directly coupled onto the integration capacitor. So
okay, actually that's actually not a bad reason. So, and let me draw this full thing over here just so that that maybe becomes more clear. Right? So what Yida was basically saying was that, well, okay, if I do things this way, then basically even when those switches are off, there was always some CGD over here, right? And in this particular case, by the way, which one of them would I be worried about from a noise coupling standpoint? Which one would be bad when it's off? And maybe I'll be, let's say, more clear. Let's say my loop filter is like this. If my loop filter is like that, what is my control voltage referenced to? Yeah, it's referenced to ground, right? Because I put ground on that cap, which is kind of implying that I want everything to be relative to ground, right? Okay, so if I want everything relative to ground, out of either the PMOS device or the NMOS device, when it's off, which one is connected to VDD? At its gate.
Up bar.
Yeah, up bar, right? So the PMOS device, when it's off, will be VDD at that gate. So what will happen is you'll just get some straight capacitive coupling directly to the output, right? Now, maybe that's not too bad. Maybe you can make that sort of ratio sufficiently, let's say, good, meaning that you can make the loop filter cap substantially larger than that coupling cap from the switch. But if you flip things over, it's not that the problem completely goes away, but now at least you have sort of, a little bit of isolation or a little bit of extra divider that comes into the picture. Okay, it depends on exactly what you believe, this VBN, exactly where you believe this VBP is and where that device sort of, let's say, leaks to once things have gone away in terms of the nominal current. But that is indeed actually one reasonable reason to do this. And actually, it turns out there may even be one more thing that you might do if you really cared about this. That actually makes this even slightly more robust. So anything else you might be able to sort of hack on this thing to make sure that, let's say in this particular case, VDD doesn't make it so easily into the output? What do you guys think?
The cap to VDD or
cap to VDD? No, well, no, wait. I mean, if you flip the cap over, then you've changed what the reference is, right? So yeah, maybe coupling to VDD is not so bad, but then coupling to everything else is kind of bad news, right?
You just make the switch in saturation region.
Okay, well, but so that is actually sort of what this VBP is trying to do, right? Because if I put this switch into, basically this VBP is just trying to bias that thing to look sort of like a quote-unquote current source, right? Is there anything else you might be able to do? I'll give you maybe a hint. Since you want this output to be referenced to ground, what would you like to show up right here?
ground?
Yeah, what if you put ground there, right? Because remember, this switch is supposed to be off, right? It's supposed to be like a current source. So indeed, you could basically do something like that, right? Just shut the thing off, right? Now, this is not entirely for free, because if you do this, you just have to make sure that basically the charge pump output voltage over here never gets close to VBP, or really never too much higher than VBP, because it does. If it does, then obviously the switch turns over and bad things happen, right? But indeed, as long as if you have reasonably, let's say, small range at the output, which we'll come back to in 1 second, then you could try and play some game like this. Okay, now, turns out this is not, let's say, too common, because if you really do want a big range at the output, then you may not really want to play around with that. But indeed, there's a couple of, let's say, fairly detailed considerations in terms of which way you're going to want to sort of put the switches. Okay? Turns out there's actually one more reason why, even if you didn't play with this game, and of course, by the way, you'll do similar things on the other side, even if you didn't add that thing in over there, there's another quote-unquote second-order thing which is a little bit different between the two. So can anybody figure out what that is? What might be a little bit different, if I build things this way versus, let's say, this way? And remember, those switches are turning on and off fairly often.
The VGS keeps changing?
The VGS keeps changing. Between what and what?
Between the two cases. The up bar.
Yeah, okay, so you're saying here we're changing the VGS of the device, whereas here we're just of the current source device, whereas here we're changing just the VGS of the switch. Okay, that is true. That's true, although I don't think there's really a way around that because we have to turn things on and off. So somewhere something like a VGS is going to have to change. But what else happens when you turn a switch? Ah, there we go, charge injection, right? So here, for this switch, right, looking down, all it sees is like the parasitic cap and maybe, sort of the output impedance of this current source, right? Looking up, it sort of sees this big loop filter. That loop filter probably has lower impedance, right? So most of the charge from that switch is going to go into the loop filter, right? Whereas over here, on one side, I've got basically the power supply, right? So I'm still going to get some amount of charge injection, but at least some amount of it is going to get swept out into the power supply. Okay? Does that kind of make sense to people? Or? Okay, so by the way, it turns out these charge pumps are actually pretty tricky. And there's a lot of sort of ways you can basically mess them up that will turn out that they are, will screw up the entire PLL. Okay, so you really do have to be pretty careful with how you build these things. Okay, so just to sort of drive that point home, turns out, like even if you do all the stuff that I said a second ago, if we sort of look more carefully at how we're really using this thing, and this time I'm going to draw the entire charge pump just so that it's sort of really clear what's going on. Okay, so this time around I'm again going to assume that I've done things so that the biases are coming in the middle. Okay, so and I'm going to draw like all of the mirrors and everything like that. All right, so I'll do something like this. And then of course these are like this. So just imagine this comes from, well, I'll draw it. From some reference current, okay? And of course, again, this is up bar, this is down, okay? And this is, again, let's say, my loop filter, okay, and that's my control voltage, of course. Okay, so let's say that you want to build a PLL that has as wide of a frequency sort of tuning range as you can get. What is that going to say about sort of what you're going to want to do with this control voltage? What do you want to do with that?
You're going to change a lot.
Yeah, you want to be able to move that control voltage as much as possible, right? So as an example, what might be the range of voltage that you like to support on that control voltage? And let's just assume that we had something like, I don't know, let's say a 1 volt supply, okay? So how much, what do you think would be a nice range of voltage for you to cover at that output there? Roughly speaking. What do you think is feasible?
2V star to VDD minus 2V star.
Okay, so you said 2V star to VDD minus 2V star. Yeah, exactly. So those are switches. That's actually another reason why this is kind of nice in some sense, is that, basically since those are switches, we can just assume there's some small voltage drop across them. So there's something like maybe V star to VDD minus V star. So let's say we use a reasonable V star. Let's say that's 100-ish millivolts or maybe 200 millivolts, somewhere in that ballpark. But that would basically say that, you want this to range from something like maybe about 100 millivolts or so up to maybe about 900 millivolts. That's maybe a little bit aggressive, but, somewhere in that ballpark, right? Well, okay. Anybody see a problem if, for example, let's say that my charge pump really was biased at 100 millivolts at the output? And by the way, that voltage is completely set by the PLL, right? Because whatever the frequency is, it's just going to drive that voltage to force the oscillator to sit at the right spot, okay? So let's say that indeed that control voltage is at 100 millivolts. Is this going to work sort of exactly the way we want? Or is something maybe a little bit annoying going to happen?
So on the on the lower end of a control voltage, your pull-down current will be lower than the...
Yeah, that's right. Basically, we're starting to squash out that bottom current source, right? So just to make that clear, right, if I look at the biasing branch, the voltage there is maybe, I don't know, approximately 600 millivolts, right? 600 millivolts or so, right? So clearly, when I do this mirror over here, the current I get through that PMOS is not at all the same as the current I got through this PMOS, right? Not to mention, of course, that the NMOS isn't really the same as this guy, because again, the biasing is just, may not be, the output impedance may not be good enough to really tolerate that, okay? So now this actually creates sort of an interesting situation. So remember, we're using this thing to kind of act like a transconductance stage, right? So let's think about what happens if, for example, I just take an up and a down signal that are totally lined up, right? Because remember, for my PFD, there's going to be always some finite width pulse that I use just so that I avoid the deadband problem, right? And let me just move this over so I've got some space. Let's say 100 millivolts and 900 millivolts. Okay, so actually, let's just draw sort of the currents. So what are the sort of I up and the I? And actually, I'll draw them on top of each other, just in different colors. So let's do that as that, and let's do this in blue. Okay? So what we're basically saying is that those two currents are not really going to be the same anymore, right? So in other words, the up, let's say maybe is going to do something like this, ideally speaking, right? And the down is going to do something like that, right? Okay, so now what's the loop going to do? Can it stay there? In other words, can it stay in this particular condition? Can't, right? Because even though you have a balanced phase input, you're pushing the control voltage up, right? Which means you're increasing the frequency. Okay, so where do things sort of have to land in steady state? Where are we going to end up? What's going to have to happen to sort of balance things out? By the way, what is the balance point? How do you find the balance point?
When I up equals I down, right? So
Oh, okay, so is it I up equals I down? Or what is the loop actually enforcing?
And the charge is this.
Ah, there we go. The loop's enforcing that the charges are equal, right? So how do I make the charge equal if the up current is larger than the down current? What do I have to change?
The pulse width has.
Yeah, the pulse width has to change. Which one has to get wider? Yeah, that's right. I down has to get wider, right? Because basically, since it has less current, you have to integrate it for a longer period of time to actually get the output to be correct. Okay, so let's actually draw that situation. And now I'll just draw the currents sort of, let's say after some time, after you converge. Or let's say after locking. Okay, so now if I again draw my I down, we just said it's going to have to be sort of, wider than it was before. Okay? So that implies that I up would have to start some time like this. Right? And presumably, if I did things right, then the area under those two curves would be the same. Right? Okay, so what do these two waveforms sort of imply about the up and down signals? Which one comes first? Yeah, down always has to arrive first, right? Because if it doesn't arrive first, there's no way for you to get this waveform, right? So again, we can draw the sort of up and the down here. That says down shows up like this, and up shows up like that, right? So in other words, this charge pump current offset is actually translating into static phase offset at the output of the PLL, right? Because again, there's no other way for the PLL to sort of lock or really get those charges to be balanced except to skew those pulses against each other, right? So by the way, it turns out you can actually sometimes use this, let's say, to your advantage. So you can intentionally skew things if you really wanted to move the phase. We'll talk about that a little bit, maybe in a couple weeks or so. But there is actually a pretty, in let's say a clock generation PLL, where you really want it to be as clean of a jitter as you can, there's a bad implication from doing this. So what's the bad implication of this? And I'll give you maybe a hint. What happens to the control voltage every time we do this?
You get a reference spur?
Yeah, you get a reference spur, right? So basically, every time you do this, control voltage, glitches down a little bit, and then, sort of gets, okay, my drawing's not great, but basically it glitches down and starts integrating down, and then actually sort of glitches up, and then, integrates for a while, and then eventually it sort of steady states, right? Once the sort of charges and everything have balanced out. So actually, it's another little glitch thing, and long story short, it comes back to the same point, right? But I've created this weird glitch behavior, right? And oh, by the way, that glitch happens every single reference cycle, even if I don't have any noise at all, right? You got a question? Or?
Yeah. So doesn't the loop filter that out?
Well, no, because remember, this glitch is happening every reference clock. And then this glitch gets fed to my VCO. And all the VCO does is says, okay, my instantaneous frequency just tracks whatever this control voltage is. Right? So yes, I mean, you can argue, I guess, that that's an integration. But again, if I keep repeating this every single cycle, then what's going to happen is that I'll see a reference spur because every, let's say, n cycles, I'll get some cycle that's long and then short and long and then short. Or for example, I'll get, let's say I do a divide by 10. On the reference cycle, I maybe get like a short cycle and then 9 long cycles. And then short, 9 long, and so on and so forth. Right?
So how is it different from getting the spurs at the output of the phase detector?
Okay, so the trick is that, remember, in the phase detector, well, no, so we did talk about last time how, in the phase detector, it too was also always making the updates on a reference clock. But remember, those movements had to do with just noise being in the system, right? So the only reason that I was making, like, say, different pulse widths was because I was trying to correct for some jitter in the first place. Right? Here, even if there's absolutely no noise, I will actually create this glitch. Right? So in other words, especially if this static, let's say the current mismatch is big, I could get a really big static phase offset, and then that reference spur will be proportional to that static phase offset and could be much larger than the noise I had in the first place. So you're right, you can't, well, okay, at least with these sort of simple types of filters I've drawn, you really can't get rid of that reference spur. Again, there are actually ways you can do it, basically with sort of sample and hold type of filters. But basically, the difference here is that even if you use this relatively simple filter, the magnitude of the error you get will be much larger simply because you're dealing with a static phase offset, which could be big, rather than just the noise signals you cared about in the first place. Does that make sense? Or? Okay, any more questions on this? Or? Now, by the way, do you think we're just going to live with this, or do you think there's something you can do to fix it? What do you guys think?
Change how the lower branch is biased?
Okay, so you said change how the lower branch is biased. You're actually going very much in the right direction.
Can you create some feedback which equates the current? Or?
Yeah, basically, right? Okay, and actually, it's not even, though you don't even have to be, let's say, that direct. But basically, you can just be, let's say, all you're really trying to do is build a better current mirror. Right? So if I want a better current mirror, or really I want the best current mirror I can get, then really all I have to do is make sure that whatever voltage I have over here, I also get that voltage over here. Right? And then as long as the devices match, then I should indeed have a good current mirror. Right? So let's just quickly sort of sketch what that would look like. Okay? So again, this is going to be sort of my main charge pump, and I'm just going to leave myself some space because I'm going to be throwing in an op amp here in a second.
But you can tolerate some mismatch between that reference branch and the final branch, right? But it's really a matter of the top and down matching.
Up and down. Well, that's right, but remember,
top and bottom.
I mean, if there's mismatch here, that will become up and down mismatch, right? Because the mismatch here has nothing to do with the mismatch here, right? Like if I just happen to throw in a random threshold voltage mismatch between these two pairs, has nothing to do with this over here. Okay, so let's just sort of go ahead and see how we can do this. So this is going to be sort of some bias voltage, and that's just going to again come from some mirror. So I'll draw that whole thing just for the sake of completeness. Okay, so I will indeed go ahead and do that. But now for this PMOS branch, how do I basically force those to have the same voltage? What do I do?
You put an op amp with the plus and minus connected to the two ends and
Right.
change the gate.
Yeah, exactly. So basically, you take an op amp, you connect one input to one side, the other input to the other side, and then you drive the gates of both of those with the output of the op amp, right? And again, just for completeness, I'll draw the loop filter over here. Okay, now I intentionally did not put any pluses and minuses just yet. Okay, so this is again one of those, let's say, fun prelim problems or something like that. Where do you put the plus and where do you put the minus? Let's maybe take a vote to see who's paying attention. So, who thinks you put the plus on the right? One brave soul. Who thinks you put the plus on the left? Only one other brave soul. Two brave souls? Okay. 3, 4. Okay, so there were slightly more brave souls for the left, so why?
I mean, right.
Say that again?
The first one.
The
The plus is on the right.
Plus is on the right or plus is on the left? So I said plus is on the right was, okay, well, here, we'll write this down. Plus on the right. How many people vote plus on the right? Now you have to raise your hand or I'll, throw a water bottle at you or something. It's plus on the right. Who votes for that? 1, 2, 3, 4. Okay, we'll go with 4. So plus on the left, and now we'll just see if we actually have, enough people in class. You guys have to vote too.
Nah, I changed my vote.
You changed your mind. Okay, so that's only also about 3 or 4. So in general, and then we have a bunch of people that I'll have to throw some water at later. So in general, how do you decide what's plus and what's minus?
Negative feedback. Negative feedback should be stronger.
Yeah, the negative feedback is the loop that you want to quote-unquote win, right? Okay, so how are you going to know which loop is going to win here?
You break both the ends of the op amp
Uh-huh.
and put a delta V source
Okay.
and see what comes back. And
Okay,
see
but
whether
so,
it's
by the
negative.
way, in this particular context, what is it that you care about in terms of making, what's going to determine which gain is larger?
I mean, the two ends, the voltages on the two ends. So
Right, no, so you're absolutely right that procedurally you break the feedback, you insert a signal one way and you measure what happens on that side. You break the feedback, you insert a signal the other way, you measure what happens on that side. But, intuitively, everything here should be matched, right?
It's the output filter.
But you have some loading, yeah.
Ah, what about the filter? What's important about that? Is it just the bandwidth?
It's making it asymmetric, right?
Okay, it is asymmetric, and what does that output filter do to that side?
it's going to reduce the impedance on the.
There we go. It's dropping the impedance, right? Now, by the way, it's actually even, let's say, better than that, because remember, there's a PLL here. So can you arbitrarily move this voltage around, given that there's a PLL feedback loop? Or no? You can't, right? Ideally speaking, the PLL makes the impedance of that node 0, right? Because that voltage has to be whatever it is to get the frequency right, okay? So now you guys tell me, where do you put the plus? And just be careful because there's one additional inversion in this loop, so So which side do you put the plus on?
The left.
Yeah, exactly. You put it on the left side. Okay? Now, by the way, just in case, there's one, let's say, simple trick for realizing it. The plus was over here on this loop. Right? But indeed, for the reasons we just described, that is where you put the plus. Okay? So basically, there is indeed a positive feedback loop here. But the nice thing is the loop filter drops that impedance A. And B, the PLL also says, no, sorry, that has to be a fixed voltage, at DC at least. Okay? Does that make sense to everybody? Or? So this is actually now starting to be a fairly common charge pump design. Because of some of the charge injection issues we talked about, you might even add some injection cancellation switches and things like that. But basically, this is indeed starting to be fairly realistic. Okay, and now, by the way, building this little op amp here is also a little bit fun because you have to be careful about the stability, and actually, because the range of voltage you want to tolerate here is pretty wide, you might need a wide input range on the op amp. But basically, this is really starting to look sort of the way like real PLLs are built. Okay. Make sense to everybody? Or? Okay, so just one other sort of quick thing that I wanted to mention, which because it sort of kind of ties into some of the stuff we've been talking about here is, when you actually build this loop filter, again, you obviously have to implement it with, some sort of real resistors and capacitors, right? So just to sort of give you some rough idea, those loop filter, the capacitor as an example, typical value for that is anywhere from about 10 picofarad up to maybe even 100 or 200 picofarads. Okay? Somewhere in that ballpark. Depends obviously exactly on the loop and things like that, but typical ballpark. Okay? So how are you going to want to build that capacitor? Like physically, how are you going to want to implement it?
Mom cap. Mom caps.
Okay, so you said mom cap. You could do a mom cap, and in fact, and as we'll talk in 1 second, you may actually have to do that, but that's going to take some space, right? And by the way, I won't be able to route anything anywhere, for like the entire block of that mom cap, right? So how else do you think you might want to do it?
MOS cap.
Yeah, MOS cap. Okay, so the good news is, remember, that control voltage generally has some bias on it. So in particular, for example, let's say I was doing a PLL that was driving like a ring oscillator, right? And let's say that, maybe the PLL was built so that I was actually controlling the power supply of a ring oscillator. Something, let's say, like this. Okay? Well, now I know that this control voltage here is going to have to be at some reasonably positive point, because otherwise my ring oscillator is going just ridiculously slow. Right? So that means that I can kind of guarantee that there should be some reasonable bias, which means that I can probably get away with actually putting a MOS cap there. Okay? So just as an example, you might build that as something like this. Okay? Now actually, so this is a little bit of fun. Why did I build it like this versus, for example, what if I had done that? Are those two different?
You have a lot of ground capacitance.
Yeah, I have bottom plate, right? So on this one, I have a bottom plate cap that sits right there. What's bad about that bottom plate cap? What does it do to you?
That's one more pole.
Say that again?
Adds a pole.
Yeah, it adds a pole, right? So if I've got bottom plate cap down there that's in parallel with the resistance, remember the resistance was there in the first place because I needed a 0. So if I now have an extra pole there, I could basically completely screw up my stability. Okay? So indeed, you typically will end up building it really so that it looks like this. Okay? So you really will put the, at least if you have like an NMOS, in fact even usually with a PMOS with caps, you'll really usually build it like this. Okay, now, turns out there is one unfortunate thing, which is that, okay, this is kind of changing as we speak, or has, but will probably come back. Some of the more advanced technologies, if you take a transistor and, you just put a voltage on the gate, you'll find that magically current actually flows from the gate either into the source or to the drain or to the body, because, again, those quantum mechanics guys just came and bit us, and we get tunneling current, okay? So what would that do in this context? What would happen to us if we actually tried to use a MOS cap with that MOS cap actually having gate leakage in it? What would that do to the PLL? Is that fine? Or is that, what's that going to do?
Frequency would drift.
Yeah, basically, if you looked at the control voltage, right, what you'd end up with is that, let's say that you nominally wanted to start somewhere, but you've got that leakage on there, right? So just start drooping down, okay? Well, if I have a droop down like that, remember, the loop is going to have to make a correction, right? Say, oh, no, oops, sorry, you weren't supposed to be there. It'll correct, and then I'll start drooping down again, right? And then again, I'll correct, right? So all this stuff we talked about, reference spurs, yet another great way to create a reference spur is just basically have a leakage path there, right? And in fact, you can imagine that, let's say that I wanted to have a really big multiplication ratio, meaning my VCO is running at a much, much higher frequency than the reference. This can get really bad, right? Because I could just be integrating that leakage like forever, okay? So indeed, in some of the more modern technologies, people actually moved to building this out of metal capacitors or some thick oxide or something like that. Maybe now if you get like high K dielectrics, maybe you can go back to the normal MOS capacitors, but definitely something to be aware of.
Can you inject current back to the node to cancel out? The
Okay, so there are at least 1 or 2 papers that I know of that tried to do that. The trick is that when you try and inject some current back to cancel it, that usually involves having another integration to figure out what's the right amount of current to inject in the first place, right? So then the question becomes, how do you build that integration? So if you do that with another cap, then you have this sort of game of how big is that cap versus how big is this cap. Now, indeed, you might be able to actually get that to work. Turns out this is actually another one of the reasons why people really started looking at more digital types of implementations, meaning where you somehow have the loop filter implemented as just an accumulator. Because there, digital accumulator, that really does not leak, at least unless you did something really stupid, right? Yeah?
I just have a question about MOSCAP. So MOSCAP is not that linear, depends on your biasing voltage.
Mm-hmm.
Does it kind of modulate this control voltage a little bit based on where this voltage is?
Yeah, so let's say there's some debate about that, but especially if I have a loop that's kind of like this, where I know that this is at a pretty reasonable bias point, the nonlinearity, first of all, is going to be fairly small. But second of all, remember, these glitches on the control voltage had better be pretty small themselves, because if they're not, that means you have a lot of jitter, right? So you're right, that does come into the picture, but I think I've never seen a PLL that was limited by that particular effect. But it's a good question.
No, but I'm just wondering, because when your VC is very low versus when it's very high, the cap is totally different. So
yeah, okay, so we're going to talk a little bit more about it, but it turns out if you really want to do things right, getting this VCO control voltage to be really, really small, meaning comparable to the threshold, you're going to have lots of other problems. Okay, so it can be done, but you're going to have a lot of other problems for other reasons that, indeed this, well, actually that effect would sort of come into the picture, but, it'll be sort of even worse than that. It's a good question. Okay, more questions on this, or? Oh, yeah.
A question on the previous slide.
Sure.
So is there any, on the bandwidth of the op-amp, is there any constraint on that?
Okay, so it's a good question. It turns out you don't have to be, depends on, let's say, how precise you want to be. To zero order, you don't have to have super high bandwidth here, only because basically you know that the control voltage is moving very slowly, right, relatively speaking, right? So in other words, you just sort of have to make sure that that op-amp is kind of high enough gain bandwidth relative to the bandwidth of the loop itself, right? And that bandwidth of the loop is limited by your reference frequency, and usually compared to sort of what you can do with the circuitry is not too hard to achieve. But you can't obviously ignore it. You have to make sure that feedback loop really is stable, meaning, or really this feedback.
So it need not be very high bandwidth. It need not be like up till the bandwidth of the loop, right? It can
Well,
be
okay, you have to
small
be a
bandwidth.
little bit careful, because if it's not up to the bandwidth of the loop, you might start introducing some, pole zero doublets and things like that. So it might still be okay, but you have to be sort of, generally speaking, it doesn't cost you that much to get the bandwidth there, and so you'll basically just do it, like just to make sure that it's kind of behaving the way you'd like it to.
But then ideally the control voltage is like sort of DC, right? So why do you need so much bandwidth?
No, well, it's true that the bandwidth, or this is sort of DC, except that it's not really DC, right? Because the loop has a finite bandwidth associated with it, right? So if your loop has 20, 30 megahertz of bandwidth, then roughly speaking, that also has sort of 20, 30 megahertz of bandwidth. Not exactly, but roughly speaking. Does that make sense to people, or? Okay, great. Okay, so now what I want to do is just talk a little bit about sort of, how you actually build some of the, let's say, oscillators. And I won't spend a lot of time on it because, that's actually, you could spend like an entire class just talking about oscillators. That's kind of not really the intent here. If people are interested, I can point you to some other references and things like that. But it turns out that, in a lot of contexts, kind of like we just drew, and for reasons that I'll explain shortly, one of the sort of fairly popular architectures these days is indeed sort of basically just use a supply regulator to just set the supply voltage of some ring oscillator. Okay, and then just use that ring oscillator to essentially act as your frequency source. Okay? So this would be like coming from the charge pump voltage. This would be like your, let's say, internal power supply voltage. And then at least conceptually, this would be sort of the oscillator, and the output, let's say, would be right here. Okay? So just a few, let's say, maybe things to note and a few questions that I'll ask you guys. So first of all, if you do something like this, you're generally going to want to put a pretty big cap right there. Okay? Because remember you might be on some, let's say, processor or FPGA or whatever the heck it is. And that's going to have 10 billion digital gates jumping around and creating all kinds of glitches on the supply. So you really want that control voltage there to be sort of as stable as you can make it. Okay, so we'll talk a whole lot more about actually some issues with how you build these regulators. But for now, take it at least for granted that there should definitely be a big decap at the output there. Okay. All right, now a couple of other, let's say, questions. Why is it that I drew this with 3 inverters before I sort of tied it into a feedback? Why didn't I do, for example, like, I don't know, 1 inverter and feed the output back to the input? What's wrong with that? Why doesn't that give me like the highest frequency oscillator I can possibly get?
Locks to a metastable point.
Okay, so you said it locks to a metastable point. So now I'm going to put on my like digital hat. So that's true. But I want to like, what was the criterion that I broke? Why did it lock to a metastable point rather than oscillating?
A digital discipline. You're hanging out in the forbidden zone.
Okay, that's true. You are hanging out in the forbidden zone, but maybe I'll ask it a different way. So what I was, oh yeah, go ahead.
The phase shift.
Okay, what about the phase shift?
What do you mean?
You said something about phase shift. What about it?
You need an external phase shift, otherwise it'll just stay static over there.
Well, okay, so not necessarily, right? So I can.
Single pole system, you never get. It's like single pole.
Okay, so you said it's a single pole system. That was the answer I was expecting somebody to give, but that's why I said originally I want my digital. Think about this in digital terms. So you're absolutely right. It's a single pole system, although by the way, it's nonlinear and has some delays and junk like that. So that's not exactly accurate, but you're right. That's kind of the, let's say, the analog explanation. What's the digital explanation?
I mean, is it because the metastable point of the 3 inverters are not the same? I mean,
no, not exactly. So let me maybe give you a little bit of a hint. So let's say that somehow magically I get this thing, I get an edge into there, right? What do I want to make sure happens if I want this loop to actually work?
With the single inverter, the gain of the loop is less than 1 because you won't actually fully charge back, right?
Okay, so you kind of went in the direction that I'm getting at, but I'm going to say it in a slightly different way. Because you still use terms like gain and stuff like that, which remember, I want just the digital explanation. Yeah.
So you want that edge to like go sufficiently high up before it feedbacks.
Yeah, exactly, right? So what you really want to have happen is you want to make sure that this edge basically gets all the way to the rail, then goes through this guy, then goes through that guy, and only then comes back, right? Because, this node that I drew right here is, of course, the same as that one, right? So in other words, the real problem with doing something like this is that essentially your rise time is comparable to the frequency, right? Because if I haven't even made it all the way up by the time I start pushing myself back the other way, that means I'm not really going to get a good, clean signal out, right? In other words, I'm going to get this, if it still oscillates, I'll maybe get some really small, little oscillation thing, and if I just get unlucky, it could completely die, right? So kind of the thing to keep in mind with all these sort of oscillators is, and this is true even in the analog domain, you really want those edges to be sharp relative to your frequency, okay? Just to make sure the thing really does actually spin the way we want it to, okay? All right, so one other sort of, let's say, question, which is, let's again say this is 1 volt. And let's say that regulated voltage can be, I don't know, anywhere from 200 millivolts, that's maybe let's be not so aggressive, 300 millivolts to, I don't know, 800-ish millivolts. Okay, so am I just going to take this clock and use it like in the entire rest of my system, or do I have to do something first? Or do I want to do something first?
put 1 more inverter.
1 more inverter. Okay, I can put 1 more inverter here. What about and now let's be okay. So by the way, so will I really do exactly just this? Is that going to work so well when the supply of the oscillator is 300 millivolts? Probably not, right? So I probably need to put some sort of level shifter, right? So I'll just X this out, I probably actually need to put a level shifter in there, right? So in other words, something that takes whatever the 300 millivolt supply was and gives me a nice, clean 1 volt signal at the output, okay? And again, this is one of those places where people don't necessarily spend a whole ton of time, and we won't spend too much time talking about it today, but again, be careful, because especially if you've got this wide range of voltage at the input, you can get all kinds of nastiness happening in that level shifter, Okay? So just as an example, what are a couple ways you could build that thing? And I'm sure you guys have seen these before. So what are a couple ways you can build that level shifter?
Source follower.
Source follower. Remember, I'm trying to go from like a variable low voltage to a single fixed high voltage. So I'm not sure how I could do it with source follower.
You have a cross-coupled PMOS and two NMOSes at the input.
Okay, you said cross-coupled PMOS. So presumably this is 1 volt, that's 1 volt. And then you said two NMOSes at the input. Okay, now what are those two NMOSes driven by?
Complementary.
Say that again?
Complementary versions of the input.
Okay, so right. So this would be, for example, clock, and then I would need another inverter there, which is still running off of the regulated supply, right, to get the complementary version. Okay, and then as an example, let's say I take this clock out. Now, I was hoping somebody would mention this particular one, because it turns out this one has some very particular nastiness associated with it. So remember, I am using this clock for a high-speed link, right? And just as an example, how was it, if you guys remember, we talked a while ago about it, but we'll actually talk about it more very soon. Pretty typical way for me to do clock recovery is to 2x over sample, right? Convenient way of doing that is just to have two comparators, one running off the clock frequency, I should say one running off of the true phase of the clock, and the other one running off of the negative phase of the clock, right? So if I just took this thing and then fed that, directly into these two comparators, is that going to be good, or am I going to be unhappy? Chintan's unhappy because I guess he had to do this once before. So anybody else? So you should be unhappy, by the way, but now we just have to figure out why.
They're not balanced.
Say that again?
They're not balanced.
What do you mean? You're right, but what do you mean by that?
The duty cycle is not 50%.
There we go. The duty cycle is messed up. Okay, why is the duty cycle messed up?
Because the drive strength is changed when the regulated voltage is changed for the NMOSes.
Okay, so I think what you said was correct, but I just want to maybe give a more intuitive explanation, right? So let's even assume that I have a fixed regulated voltage, okay? So in order to cause this thing to rise, what do I have to do? I basically have to make this go high, right? Which pulls this down, which then turns on that PMOS, which then finally makes this go high, right? In contrast, to make this go low, I have to go through this inverter, which is on the regulated voltage, then turn on this NMOS and pull that node down, right? So in other words, the delay from those two paths, completely different, right? And that's, of course, even just at 1 voltage, it'll be wrong. If you change that voltage around, it'll move around in terms of how wrong it is, right? Yeah?
So why can't you tap out from like one more stage before rather than putting on one?
You absolutely could, but you'd still conceptually have the same problem, right? Because there's a phase shift between this output and this output, which is not exactly 180. And even if it was exactly 180, you would still not get it right, right? Because notice this has like, two, let's say, stages in it, and this only has one, right? So in fact, in some senses, this is slightly, the fact that they're not exactly matched sort of helps you a little bit, but again, it's apples and oranges, right? So actually, if you really wanted to do something like this, what you'd probably have to do is actually build 2 level shifters, okay? Where one, you just sort of take the bar output versus the other, okay? Each individual duty cycle would still be wrong, but at least the rising edge to the rising edge would be the same, right? So again, this is in general, you have to be careful anytime you do these level shift kind of things. And okay, I guess I see some confused looks. So all I'm saying is that basically, if one time I treated this as being the true output, right? And I basically took clock and fed clock bar over here. For the other one, I just feed clock bar here and clock there, right?
How can you get the clock bar?
Same way I got it here. Just by looking at 2 different stages, for example.
So you just put 2 completely separate clocks.
Well, I mean, I may take just multiple outputs from here, right? Multiple outputs from the ring. You see what I'm saying? Or
I guess what you were saying earlier was that you have one clock, like one of the level shifter produces clock and the other one produces clock bar.
That's right. So if I just flip which one I called clock and which one I called clock bar here, then that would do that, right?
But then you're distributing two different clocks to the serial link, or
Well, one clock goes to here, and the other clock goes to there. Yes, that's right.
isn't it just better to, okay, I mean, just split one clock and...
Okay, so there are other ways you can do this. Don't get me wrong. So in fact, what people will typically do is they may do this, and then even after they do this, they may put a duty cycle corrector afterwards. Or you may just try and build a different level shifter. Or you may try, do something where you use one edge to like drive the output high and the other edge to drive the output low. But by the way, even that is not perfect because there's always mismatch in those processes.
So why is the duty cycle not 50% starting? I don't quite get it.
Oh, because remember, I didn't do anything to change. Like if I looked at the duty cycle of each individual clock, I didn't do anything to fix that, right? So if I draw these waveforms, for example, if I looked at, let's say this is clock O, and this is, let's say, clock O bar, right? What I'm basically saying is clock O might look something like this. Clock O bar will look something like that. So in other words, each individual duty cycle is still wrong, but the spacing between the two edges will be correct. Okay? And in this particular example that I've drawn here, having at least the spacing between the edges be correct is better than, having both the bad duty cycle and the incorrect spacing. Does that make sense? Or more questions on this? Or
There's a...
yeah, go ahead, Linkai.
So the clock inside the ring oscillator is not 50% duty cycle from the beginning, right?
Okay, so now that depends on how you've actually built the ring oscillator.
Right.
So the question was, is the clock even 50% to begin with? You're absolutely right. It may not be, right?
Okay. I'm just saying.
Turns out you will typically try and size things so that it reasonably stays 50%, just because for phase noise that turns out to be a good thing to do. If people are interested, come bug me. I can explain why. But you're absolutely right. It may not be 50% to begin with. That's absolutely correct.
And inside, like if it's a 3-stage, where did you get the clock bar? Because there's no 180-degree phase.
That's right. I won't get. So that's what I'm saying is I won't really get clock bar. I'll get clock bar plus 60 degrees or whatever it is.
Great. And then when you choose two parts, how do you get the clock and the clock bar from the beginning?
Oh, okay. So if I really did it, then I would probably just phase split or something like that, and then use.
Then that phase splitting depends on the supply voltage, right?
Yeah, that's right. So by the way, there is no perfect way to do it. Okay?
No, just
So,
make sure.
I mean, what you can also do, which is slightly, let's say, more common, you could just have one level conversion path, let's say something like this, right? And then phase split, at least in the full supply domain, so you have less variation in terms of what you have to deal with on that phase split path. But again, there's actually no perfect way of doing this. Okay? Yeah?
Well, some of the VCO I remember seeing in the past, they are like fully differential.
Okay, we're going to talk about that in 1 second. So there are VCOs that will give you what should be differential signals, but by the way, even there, they will mismatch, right? And again, actually, we're going to draw that in just 1 second. But in general, there's no perfect way to do it. There's only sort of, let's say, getting it close enough. And then if you really, really care, you'll tend to end up building what's called the duty cycle corrector. So you'll actively try and correct those phases. Okay? That's, by the way, even that loop has lots of things that you can't do perfectly either, but if people are interested, we'll talk about that one a little bit later on. Okay? Okay, so as Charles was asking about, turns out that oftentimes you won't just do a ring oscillator the way I drew it. You'll actually build basically a differential ring oscillator. Okay, so there's lots of different reasons why you might want to do this. One is just getting the differential phases like we just talked about. But actually, even independent of that, sometimes you'll want something like a multi-stage differential ring, just because, as an example, another fairly common technique is to run the link at what's called double data rate, meaning that essentially on both the rising edge of the clock and the falling edge of the clock, you try and grab data, right? But if you sort of think about what it would take to then also recover the timing information, that would mean that you'd also need a quadrature clock, right? Because this would end up being half a bit time away, right? That would be, let's say, t-bit over 2 if you do the quadrature clock there, okay? So oftentimes you actually want to build sort of these more complicated rings just because you want actually multiple clock phases to sort of essentially get everything that you need in terms of all the information in the rest of the link, okay? So one of the most sort of common ways of doing that is essentially to build, especially if you want this quadrature, which turns out to be a fairly common thing to want, is to essentially do these sort of differential ring oscillators. Okay, so the basic idea is that if I take, let's say, 2 chains of 4 inverters, and let's say that somehow magically I know that this is inverted from this. Okay? Well, if I know that that's the case, then what I can basically do is, when I take the feedback, normally if I had 4 inverters in a row and I just directly tied the feedback, it would just latch, right? But if I know that these 2 chains are inverted from each other, then what I can do is just cross over. Right? And now this thing should indeed oscillate with an even number of stages. Right? Now there's just one quote-unquote minor caveat. So what's the quote-unquote minor caveat here? Is this guaranteed to work?
How do you make sure that you start off with the inverted?
Yeah, how do you make sure that you start off actually with the bar of, the signal on one side versus the other? Okay? So it turns out you can actually ensure that. The way you ensure it is you literally just throw something in there that forces it to be that way. Okay? So the most common way to do that is basically just to add some cross-coupled inverters like this. Now, by the way, can I really just add it in one point like this, or do I have to actually add it everywhere? Yeah, you have to add it everywhere, right? Because remember, you wanted all of the phases to actually match, right? Because you're trying to use all of them, right? So indeed, now I have to start adding this in every single point. Okay, so it ends up looking something sort of like that. Okay, and then again, just to make sure sort of everybody is clear as to how this thing works, if I called that one right there 0 degrees, okay? Actually, sorry, let me shift it back by 1. If I called this here 0 degrees, okay, then that would sort of say that this is 180 degrees, right? And now each inverter delay basically gives you 180 plus a 45-degree phase shift, right? So in other words, this would now be 225 degrees, and this would be 45 degrees, okay? Similarly, this would be 90 degrees, and this would be 270 degrees. Okay, this would be 315, and this would be 135. Okay? Does this make sense to people, or do you see why I'm sort of zigzagging? Eric, you had a confused look, so.
Why is 180 plus 45?
Because these are inverters, right?
Yeah.
When I invert, then that's basically saying that I did a 180-degree phase shift.
Yeah.
So that's why now the 45 is just because each inverter also has delay. So if I had a 0 delay inverter, it would be 180. Now, and the way I got 45 is just that, notice it takes me essentially to get through this ring. I have to go through this upper path, ring around here, the lower path, and then come back. So there's 8 of them per clock cycle. So that's where the 45 comes from. Okay? All right, so this is indeed actually a fairly common technique. As we were sort of implying a second ago, because I actually want to use both the 0 degree and the 90 degree, and I really want them to be 0 and 90 degrees, I really have to make things match, right? So that means that all of the level shifting, everything that I do on this stage, I better also do here, right? And in fact, typically you better almost always do it here and here also, because if you don't, you're likely to get some mismatch. Okay? So this can indeed be done. Turns out to be a little bit of a pain in the butt just because there's a lot of matching considerations to really get it right. But, is not, let's say, the end of the world. Fairly common technique. Okay? There is, however, one penalty that we do pay here. In fact, well, maybe 2, but really one sort of important one. So when I add these cross-couple inverters here like this, is that a good thing or a bad thing from the standpoint of speed, power, etc.?
Use of frequency.
Reduces your frequency, right? So now for the same clock frequency, basically you're going to have to up that power supply voltage, right? So you have to spend more power, not to mention that, of course, you have crowbar currents because they're fighting each other. You have more capacitance, right? This forces you to sort of size things with a certain ratio, right? Because if you don't, then again, the whole thing may not work, right? So indeed, it basically slows you down, okay? And remember, if I'm trying to do, let's say, a 10, 20 gigabit per second link, and I really wanted to do it with a ring like this, I really want to push on the frequency of that oscillator, right? because I want to get this thing to go just as fast as I can go. Okay? So, turns out there's one actually very interesting trick that you can play that still enforces the things to be differential, but actually allows you to make the ring faster than it used to be. Okay, so this sounds really weird at first, but I'm going to sort of draw you, let's say, conceptually how you might be able to do something like that. So just because the drawing gets a little bit complicated, I'm actually going to do this with a delay line instead of with a ring oscillator, but you can basically do the same trick. Okay? So let's again just take, our chain of inverters that we used to have. Okay, something, let's say, that looks like that. Okay? And so again, let's just imagine that somehow I have clock, and I have clock bar right here. Okay? So conceptually what we were doing before was we were adding another inverter kind of in parallel with that main inverter. Right? At every one of those stages, we had another inverter that was like somehow going to enforce that we actually got the right differential condition. Right? Okay, so what we did last time was the input of this inverter here, we basically tied to the output of that inverter. Right? But that was kind of guaranteeing that things slowed down. Right? It was kind of guaranteeing that we had to fight this inverter to actually move forward in time. Right? Well, guess what? If this is 180 degrees, or at least I should say, if this is logically inverted from this one, then guess what? This should also be logically inverted from this one. Right? Logically, again, ignore the delays for 1 second. Okay, so what if instead of grabbing that output, I instead actually grab this one and connect it over like that? Okay? And similarly, I grab this one and connect it over like this. Okay? And by the way, you'll do this, of course, in every stage. Okay? Well, so the idea here now is that I'm still going to guarantee that things are inverted from each other. Right? Because I've sort of, by adding those extra little inverters, I've made it so that it's really hard for you to start up in a position that was bad. But now notice, this thing starts transitioning before this one even does. Right? Or really, actually, to be more precise, this starts transitioning before this inverter actually gets its input signal. Right? But it is actually moving in the right direction. Right? Because you know that, for example, if this starts going high, you know that this is at some point going to have to go low. Right? So in other words, what we're basically doing, because we know that, by the way, we will eventually tie a ring around this whole thing, because we basically know that we have a signal that's earlier in time, what we're basically doing is we're trying to use that signal to speed this inverter up. Okay? It's basically sort of like, it's almost like we're predicting that it's going to have to move eventually. Yeah, Charles?
But would actually mess up your duty cycle even more, because right now it really depends on the ratio this tube has?
Not necessarily. Again, it sort of depends on how you size things, because remember, at the end of the day, I'm going to close this into a ring. Right? So everything is going to be sped up on both edges because of the coupling that I'm doing. Right? So it's not necessarily actually going to change the duty cycle sort of any much more than this one did.
I guess my question is really about how do you actually size this main inverter, and this is...
Okay, so that's a really interesting question. And by the way, I should mention, they didn't call it this, but this technique is known as phase forwarding. Okay, it's also sort of, you can kind of think of it as also basically you have coupled oscillators. Okay, because if you sort of think about this, like when I start drawing these extra connections like this, you can start figuring out other rings that the signal could be flowing through. Okay? So the original work on this was sort of, they thought of it as being a coupled oscillator. This was done by a guy named John Matiadis. Okay, this was his PhD thesis. And I forget, this was back in the sort of late 90s or so. Let me see if I actually wrote down when it was. Yeah, it was maybe even actually early 90s, excuse me, like maybe 91, 92. Okay? So basically what he showed was that if you took a whole bunch of different ring oscillators and coupled them in smart ways, you could essentially guarantee certain modes of overall oscillation, but actually get sort of the equivalent of gate delays much, much less than a fan out of 4. Or really much, much less than what you could have done without doing these kind of coupling tricks. Okay? So if I remember correctly, he was working back in like maybe even half micron technology or so, and he was getting things in the sort of, 10-ish picoseconds of delay, or I should say phase resolution. Maybe even sub that.
Just a following question on this thing. When I actually see the title, I was actually thinking about you actually might talk about Mike Chang's work. They actually use resistor to do feed forward.
Did you say Mike Chang? Or?
Yeah.
When was that?
ISCC 2009.
Yeah, so this guy was 1991 or 2.
Right, but I guess my question was, how does it compare using inverter for feed forward with using resistor for feed forward?
Same idea. Very similar idea. So the question was just, how does it compare to using an inverter versus using a resistor? Basically, it's the same thing, right? The resistor just changes whether or not you've inverted to begin with. But conceptually, you have to size that resistor so that you guarantee that you're in the mode that you want to oscillate, right? And then depending upon sort of, let's say, the relative weight of or the relative strength of that resistor or inverter compared to the main path, that will sort of set how fast, really how much you've sped up the overall operation of the ring, okay? So there's kind of this dual constraint of guaranteeing that the thing still works. Because you can imagine if you make like a chain that only has effectively 2 inverters in it or 3 inverters in it, that would be like just, would fail our original like rise time versus frequency constraint, then it won't work at all. But you could sort of back off a little bit from that and still make, let's say, this mode the dominant mode, but just speed all of the inverters up by some fairly large fraction. So that's really sort of how you have to go about doing the sizing for these kinds of things. Does that make sense? Or, by the way, this is more generally sort of how you do what's called phase interpolation. Okay, so more generally, let's say that you do indeed want to do something that has a variable delay or a variable, let's say, clock phase. Well, what you can actually do is just take 2 clocks, for example, some clock and some delayed version of the clock, right? Just feed them into 2 inverters. If you short their outputs together, then indeed you'll get something that its delay is somewhere in between the delay of the 2 inputs. Okay? I'm not going to dive into this in too much detail now because we're actually going to have a whole lecture just on how you really build these things. But conceptually, you can kind of see that just for the same reason we said here, where one clock was earlier than the other and it pushed it in the right direction, same idea here, right? If one clock is earlier than the other, then it sort of pulls that late clock to be earlier than it used to be. Okay? Does this make sense to people, or? Okay, so since we talked about ring oscillators, I guess I just have to throw in, let's say, one obligatory slide about LC oscillators, although, to be honest, you guys might actually end up using them, because if you really want to hit the sort of 10, 20 gigabits per second, that's a fairly common sort of architecture to use. I'm going to assume that you guys have seen these a whole bunch of times before, but just, again, for the sake of sort of completeness, very common sort of LC oscillator would essentially just look something sort of like this. And again, there's obviously many, many variations on this. But again, the idea here is just that, and I'll add, let's say, one important thing, which is, because we are doing this inside of a PLL, you're going to have to tune something. Generally, you're going to tune the capacitance. But of course here, the general idea in this kind of oscillator is that what you're trying to do is just, if you had some RLC sort of parallel network, well, that R is just representing the loss in the network. Well, all you're really trying to do is put a negative resistance in parallel with that loss just to make sure that basically it's perfectly an oscillator. Okay? So again, I'm going to assume you've seen these a whole bunch of times before, or at least once or twice in, let's say, 142, 242, something like that. People have questions, just come bug me, but that is indeed sort of the basic sort of thing that you might end up using. The only other thing maybe that I will mention is that this thing here does indeed have to be tunable. Okay, so you might do that, for example, just by building a varactor, and in this particular thing, if you really want it to be differential, you may do something like, as an example, this. So that might be your control voltage, and then this might be, let's say, V plus and V minus. So that's V plus, that's V minus. Okay? Again, whole big body of literature on really exactly how you do this and what are more considerations and stuff, but just for the sake of completeness, I wanted to put it here. Any, let's say, quick questions on this one, or people are good? Okay, good. So obviously what you can basically do is just either build a ring oscillator PLL or build an LC PLL. Just really quickly, why might you want to do one versus the other? Why might you want a ring PLL? What's nice about the ring?
Okay.
Say that again?
Small area.
Yeah, it is indeed very small. It's compact. What else? Frequency range. Yeah, exactly. Okay, so what's really nice about the ring is even though I said that you had to build a 10 gig link, by the way, if you actually were to go out, in industry, whatever that 10 gig thing that you built would probably also have to run anywhere from 0 to 10 gig. Okay? So the ring, really, well, I shouldn't say really, but generally much, much easier to do that than with something like an LC, right? Because with the LC, you'd have to get that tank to move around by this huge amount, which means you have to have hugely variable capacitors, which turns out to be a pretty hard thing to do. Okay? So kind of the downside on the LC is relatively limited tuning range. Now, I guess that same downside is also sort of a plus, because that also tends to mean that you sort of know where everything is. Right? Everything's kind of centered around one spot, and you don't really have to worry too much about it moving around. Right? Because even if somebody went and tried to vary it, usually, okay, process maybe gives you, I don't know, plus minus 10% or so here. Right? But on the ring, because I can tune it, that also means that things that I don't want to tune it will tune it. Right? In other words, if I just give you a different process corner or a different temperature or a different supply voltage or really actually a different phase of the moon, it'll move. Okay? So now, just to give you an idea, roughly speaking, you can easily get like, well, okay, maybe that's a little bit aggressive, but not too uncommon that you can get easily about a factor of 2x range in that ring at a fixed voltage. Okay? So if you start moving the voltage around and the process and the temperature and etc., you can actually pretty easily end up with 3 to maybe even about 10x sort of range of things that ring might be dealing with. Okay? This turns out to have some pretty, let's say, interesting implications in terms of how you'd actually want to build the PLL. Okay? So let's actually think about that a little bit more carefully. Okay, so if I just sort of, take that ring oscillator, and okay, I should have put, 1 plus here, which is, of course, good phase noise. Okay, that's obviously kind of important. Okay, well, ring oscillator, the oscillator itself tends to be dirty. Okay, and kind of the reason it tends to be dirty is that, again, since everything and its brother can move it around, it will. Okay? So if your ring oscillator tends to be dirty, and this is something, we'll get into in a lot more detail next, but you can kind of imagine if the ring oscillator tends to be pretty dirty, that tends to mean that you really want to have as high of a bandwidth as you can in your PLL loop, right? Because the higher the bandwidth of the PLL, the more it'll sort of reject all of the noise coming from that ring oscillator, right? Okay, so let's go ahead and say that we, just draw like the transfer function of our PLL from the reference, okay? So that typically, again, looks something sort of like this, right? So if I want as high of a bandwidth as I can get, where am I going to, by design, where do I want to put the bandwidth, roughly speaking? What's kind of the highest I can reasonably get?
1/10 of the reference.
Yeah, something like 1/10 of the reference frequency, right? I'm going to want to put this at roughly omega ref over 10, okay? All right, so now here's where we start having some fun. So I just said that at a fixed point, process or temperature or something like that could move the frequency of the oscillator by easily a factor of 2. If I move the frequency of the oscillator by a factor of 2, what else is going to vary that may cause you some unfortunate problems? I'll give you guys a hint. The way I got this bandwidth was by saying something like, okay, I had a phase detector, right? I had some loop filter, and then I went through some VCO. There we go, right? KVCO also varies. And in fact, it can vary a lot. Okay? Well, if the KVCO actually can vary, and can vary quite a bit, what's going to happen, for example, if the KVCO got larger and I set my nominal loop bandwidth to be 1/10 of the reference frequency? What's going to happen?
Want to reduce? Or reduce?
if I increase the KVCO? So remember, by the way,
bandwidth, so you can be unstable.
Yeah, it's gonna. So if I increase the KVCO, that's kind of like saying I've increased the forward gain here, right? So from an open loop standpoint, I'm pushing out the crossover. Well, and if I've got some third order pole or just my sampling frequency or whatever sitting there and creating some large phase delay, if I increase that KVCO, well, guess what? This thing will just go bloop off to infinity, right? And you'll be unhappy and nothing will really work, right? Okay, so now if you really had to do this design, given that you know that it varies, now what do? Where do you put that bandwidth? And by the way, I'll say that, let's say the KVCO can vary by, I don't know, plus minus 100%. So let's say it can be a factor of 2 larger or a factor of 2 smaller. Where are you going to put the nominal loop bandwidth?
20.
Where do you have to put it? Oh, I guess you did say it. Just speak up. Yeah, okay. So because it varies by a factor of 2 in either direction, what I have to do is make sure that in the worst case, if KVCO is as large as it possibly could be, I'm still stable, right? So that means that nominally I have to back off by a factor of 2. Okay, so I'm going to put some nominal curve, let's say like this, put that in omega ref over 20, so that just in case, if, for example, my KVCO is 2 of the KVCO nominal, that would, let's say, look something like this, okay, where that has omega ref over 10, right? But oh, by the way, it could vary in the other direction too, right? So if it did that, then I would maybe get something like this, which would give me only omega ref over 40. Okay, so now what's the bad news? Bad news is, okay, fine, so I can get this thing to work. I'll guarantee that it never goes unstable. But in the worst case, I better margin for my performance to be at omega ref over 40 instead of omega ref over 10, right? So you can see I'm paying a huge penalty in terms of the effective loop bandwidth I can actually get. Okay? So this is actually a very real problem. It turns out that because of this, there was a whole, let's say, line of work that people did just to try and make sure that you can actually get omega ref over 10. Okay? So we won't be able to go sort of all the way through this, but we'll start actually talking about it today. Okay, so, oh, yeah.
I just got an additional question about this K for the digital VCO. I remember someone actually told me like it's really not linear, right? Does that actually have any kind of implication?
Yes and no. So I mean, in this particular context of setting the loop bandwidth, I'm sort of saying that the linearized KVCO could be moving. Now, what's true is that, by the way, I may want to use this PLL with 10 different reference frequencies, or with 10 different output frequencies, right? So then if I start doing that, then it's even worse, right? Because then I have to sort of put the bandwidth at whatever the worst possible thing that could ever happen to me would be. And by the way, I focused on KVCO, but hey, this loop filter varies too, right? Charge pump actually varies too. Everything varies, right? So again, kind of because of all of those reasons, there was a pretty big line of work that was actually also happened to be done by, or at least started by, John Maniatis. And I believe he sort of first published some of the things here in JSC in 1996, where the basic idea was what you want to do is somehow figure out a way to make it so that you basically adjust your loop components so that basically what you get is that the loop characteristics, so meaning the bandwidth as well as, let's say, the damping or the phase margin or so on and so forth, all basically are set by two things. One, you want them to be set by whatever your reference frequency is. Okay? So in other words, I want it to in other words, what I'm trying to say is that, if I have a certain loop band, if I have a certain, let's say, reference frequency coming in, I always want my loop bandwidth, for example, to be 1/10 of that reference frequency, or 1/5, or 1/20th, or whatever the magic number ends up being. Okay? The other thing that it's going to be sort of set by, well, maybe you guys can guess. What else am I going to have to set it by? How am I going to sort of set things to be 1/10, or 1/20th, or 100th, or something like that? in general in CMOS, when you want to do things and make them work well, what do you have to sort of slave them to? How do you make a good voltage divider, for example?
Matching.
Yeah, you want to make things be set by ratios of identical components, right? So in other words, you want this to be set by ratios of, for example, capacitors, resistors, etc. Right? The exact physical components you use to ratio actually is not so critical. We'll see that typically it will end up being ratios of capacitors. But basically, the whole idea of self-biasing is making it so that indeed your loop bandwidth tracks with the reference frequency and tracks with just ratios of physical components. Okay, so you can actually build something that you believe really will land where you want it to be. Okay? There's actually a third thing here, which is the divide ratio, but that's just a number which you can program, so that's not too big of a deal. Okay? Does this kind of make sense to people, or? Okay, so we're basically out of time for today, but next time we'll pick back up with this, and we'll see that indeed you can actually do this. So see you guys in about a week and a half or so.